All right, so there were some recording issues, so this is take 2. This is Math 150 multivariable calculus, lecture 19. As remarked initially, this is the hottest lecture of the semester, I think, because it's been a 2-week break. So it is a little bit of a challenge to get back into the mindset of classes. This is why, not coincidentally, all the material we're doing today is material we have seen before. And so there will be a lot of homework problems due Wednesday, but as always, the TAs and I are available. So the 3 things I want to do today is I want to talk a little bit about level sets. For the most part, this is the 21st century. If you have to plot something, what are you going to do? Use a calculator, use some kind of software program. You're not going to be doing this by hand. So you need to be able to know enough so that you can get a rough sense by looking at things as to what it looks like. You should have some idea. You should know what a level set is. But for the most part, anytime you're going to do anything, you're going to use some kind of software package. And so in the notes below, I will have Mathematica code to do this. You do not need to use Mathematica. You can use whatever you want. I use Mathematica because that's what I first used, and there is a huge advantage to whatever you use first becoming your standard. We'll talk a little bit about limits. A lot of times limits are not so bad if you just substitute in the value that you're approaching, that point that you're approaching for the variables. If things are nice, that gives you the answer. Most limit laws are what you would expect. The limit of a sum is the sum of the limits. There are a few technical issues that we'll talk about. And then the last is just reviewing partial derivatives. So if you have a function of several variables, you have a little bit of freedom. If you have only one variable, if I want to take the derivative, well, there's only one variable in play. So I'm going to take the derivative with respect to x. And you've hopefully heard that phrase, with respect to x, when you take Calc 1. In some sense, it's really not necessary when you're doing Calc 1 because there's only one variable at play. You can just say, I take the derivative. We say with respect to x to prepare you for Calc 3 when you now have other variables you can use. And so when you take the partial derivative with respect to x, that means hold all the other variables constant. So you just pretend that y, z, whatever you have is a constant, and you just differentiate with respect to x. So use the same rules as before. Use the product rule as before, the quotient rule as before, the chain rule as before. The question then becomes, as you have more and more involved derivatives, what do they mean? So in one dimension, if the first derivative is positive, what does that mean? So if the first derivative is positive, what does that mean? So you should always have some kind of physical interpretation. Let's say f of x represents your location at time x. What does f prime of x represent? Okay, but what physically does that mean? If f of x is distance, what's f prime of x? Velocity or speed. So if f prime of x is positive, what does that mean about my speed? I'm moving to the right. So my distance is increasing if I move forward a little bit in time, and it's decreasing if I move back a little bit in time. What if my first derivative is negative? Then it means I'm decreasing my distance from home if I move a little bit forward in time, and I'm increasing my distance from home if I move back a little bit. What if my first derivative is 0? What does that mean? I'm sorry? I'm not moving at that instant. It doesn't mean that I have a maximum or minimum at that point. If I give you the function x cubed, this function has first derivative 0 at 0, but it also has second derivative 0 at 0. And so at that point, your speed is actually going to be positive a split second after 0, and it's going to be positive a split second before 0. What's the derivative of x cubed? 3x squared. So the only time, something has happened here. The only time, just move it down. Okay. The only time your first derivative will not be positive for the function x cubed is at x equals 0. Every other time your first derivative is positive. So we have a nice geometric interpretation of the first derivative. We have a nice geometric interpretation of the second derivative. Now that we have more variables, well, what does it mean when I start looking at a vector of partial derivatives? What is the geometric interpretation? How do I find candidates for maxima and minima? What is the second derivative? How does that generalize when I now have multiple ways I can take derivatives? I can take the derivative with respect to x twice, or x then y, or y then x, or y twice. How do I put all of these together to get an analog of the second derivative test? How do I put this together to get an analog of the first derivative test? So that's the big stuff we're going to be leading up to. But for today, all we want to do is, what does it mean to take a partial derivative? Well, very simply, just consider every variable fixed but the one that you care about. All right, so that is the high-level overview of what we're going to do today. All right, so the first, just does not want to move today. All right, so the first thing is just defining again, what does it mean for a level set? So to me, I like to think of level sets as it is the set of points a given height above ground. So if you think of a mountain, I'm thinking of all the points on the mountain that are a given height above ground zero. So I'm looking for all the inputs that are sent to a given level for output. So if I have a map like this, I'm looking for all of the xy such that f of xy is a fixed height above the xy plane. So if I'm looking in Williamstown, I might want to look at all places that are 20 feet above Hoxie Street. If this building was level, you might actually have just the floors of all the classrooms in this building. I'm not convinced that this building is level relative to Hoxie Street. But in this classroom, what do you think might be a reasonable level set? I'm sorry? I'm sorry? 3 feet. Okay, can you give me something physically that might be 3 feet?
Like the chair, the seat in the chairs.
Yeah, maybe the seat of the chairs. I mean, the chairs go up and down a little bit, so I'd probably use the writing table on the chairs. But something like the chairs, I think, would be a reasonable group of things. And so if I drew a plane 3 feet above ground level in this room, it should be intersecting the tops of those. If I move it up to 3.5 feet, I'll probably be intersecting, all of us, somewhere above maybe the belly button. If I do it at 7 feet, I'm probably not going to get anybody here. Even if I have a basketball star, people are sitting down, so I'm not going to get anybody. So what would be the level set? It would be empty. So if I give you a function of one variable, is it easy to plot it and see what it looks like? Yeah. If I give you a function of two variables, it's not so bad to plot and see what it looks like. It's a little bit harder because it's actually going to be, in some sense, a three-dimensional object. The input is going to be the xy plane, and the output, how high the function is going to be z. So the plot of a function of two variables is actually going to be something in three-dimensional space. I think you can probably see where this is going. What's the next thing we would try to visualize? So we had a plot of a function of one variable, a plot of a function of two variables. What's next? 3 variables. Yeah, good luck with that one. There are some tricks you can do. You can try to use color to represent something else. And maybe I have three-dimensional space, and then for each point in three-dimensional space, I color it. Maybe if it's a dark red, it's really positive. Maybe if it's a dark blue, it's really negative. Something like that. You can try to play games like that. The other thing is, has anybody here ever watched streaming video? Does it look like you see three-dimensional action happening? Do you have a three-dimensional box when you're watching streaming video? It keeps adjusting things today. It's not my day. So when you're watching video, you don't have a three-dimensional cube or box in front of you where you're seeing the action happening. You're seeing a projection, in some sense, down onto a two-dimensional plane. So you are seeing a three-dimensional movie projected onto a two-dimensional screen. We can do tricks like that and project four-dimensional things into maybe a three-dimensional space and play some games like that. At some point, however, the tricks will fail. If you want to try to imagine a 26, we're not going to do a 26-dimensional object. And this is where math formalism comes into play. Rather than trying to visualize things, and it's wonderful when you can visualize things, at some point we just roll up our sleeves and we just work with things formally. And so the level sets will be all the inputs that go to a given output. There's lots of different ways you can try to represent it. So, here, the image on the left is a picture of, say, two mountains and a plane cutting through. And then you look down here, and that's going to be the level set of height C. It's going to show you which points in the XY plane evaluate to C under F. And if you choose a different function or you choose a different value for your height C, you'll get a different level set in the XY plane. And that'll just be all the inputs that go to a given output. On the right is another more interesting one, like a hyperboloid. And they're projecting down here, and you're looking at these lines, and these lines are places of constant height. When you look at this, it gives you a lot of information as to what's going on. The more times you look at something like this, the easier it is to understand what's going on. One of the difficulties of looking at what's going on here is it's tough to tell, well, what are the different values? So over here, they write C equals, I think that's 30, and C equals 30 over here to just give you some sense. Or is one of them negative 30? That might be, okay, that's negative 30 over here. So the ones where the y-axis is cutting it, that's negative 30. The one with the x-axis is cutting it is positive 30. And you can see, yes, it's going really high up in one direction and it's falling really fast in the other. The more labels you have on what the value of these lines are, the better. What do you think the value is where the two lines intersect? So it's x squared minus 3y squared. What do you think the value is where the two lines intersect? I'm sorry? Yeah, I think that's 0 over there where the two lines intersect. And then just trying to get a sense of, what are the values of the different lines? Okay, well, I think as, if I keep x equals 0, as I increase y, it's going to get more negative. So when I'm coming down the y-axis, the value of C is getting more and more negative as I walk down the y-axis. What happens as I walk up the x-axis? As x becomes larger and larger and larger for x squared minus 3y squared. What would that be? What would happen to the value as x becomes larger and larger and larger for x squared minus 3y squared? It gets bigger, right? X squared minus 3y squared. When does x squared minus 3y squared equal 0? Well, I can factor that as to x minus root 3y. Let's see if I can write here. So I can factor this as x minus root 3y, x plus root 3y. And if I write it like that, if x equals root 3y or x equals negative root 3y, the value of my function is going to be 0. Oh, so when I look at these two lines intersecting, that's going to be the level set of 0. And so just looking at this picture down below, I get a good sense of what's going on. And the idea is to be able to quickly get a feel for what's happening. When you look at it, does it look like those two lines are, at 45 degrees? Does that look like maybe y equals x and y equals negative x? When I quickly looked at that, I thought that they were 45-degree lines. It's sometimes a little bit hard. We don't necessarily have x and y being drawn on the same scale with something like this. So I think I showed you the XKCD joke about, we should break up. Yes, I can do better than somebody who doesn't label their axes. When you don't have axes labeled, when you don't have things labeled, it's sometimes very hard to look and see what's going on. You can get a rough sense, but they may not have the x and the y scale the same over here for this one. Okay, so here is another example of trying to show some functions and just trying to show the level sets and giving you a sense of what's going on. If you look at the blue mountain over here, as you're going higher and higher and higher, the mountain is getting thinner as you ascend. And so the size of a level set of a given height is going to be getting smaller and smaller and smaller. And so when you look at this, when you look at these circles, you will see that it's getting smaller and smaller and smaller. You've probably seen maps like this. If you look at temperature maps of the US, you might see lines of constant temperature. Anybody know what we call those lines? ISO? You sometimes do this in chemistry. Isotherms, I think lines of constant temperature. You might also see lines of constant pressure. I think those are the isobars. But the goal is to be able to just quickly look at something and get a flavor. All right. So if I give you the function cosine of x squared plus y squared, let's try to figure out what the level set is. So I want to know, so I want to solve for x and y such that cosine of x squared plus y squared equals c for a fixed c. Can anybody tell me some values of c where this is going to be really easy to solve? I want the cosine of x squared plus y squared to equal c. Give me some values of c where you can immediately tell me which x and y can work or not work. Okay, but there's something much easier than 0. Much easier than 1. What can you tell me about values of cosine? I'm sorry? Nope, something much easier than -1. 2, right? What x and y will give you a cosine of 2? Nothing. So we know it's empty if the absolute value of c is greater than 1. It's really easy to analyze the level set when c is greater than 1 in absolute value because we know cosine lives between -1 and 1. As soon as we are stuck with c between -1 and 1, now it becomes a lot more work. But this depends very weakly on x and y. It only depends on how far you are from the origin. So what can you tell me about the shape? So it only depends on the distance from xy to the origin. So what can you tell me about the level sets? What kind of shapes will they be? Circle. Actually, it's going to be a union of circles. So level sets are union of circles if c is less than or equal to 1. So for example, if c equals 0, when, well, let's do c equals 1. So what has a cosine of 1? So what has a cosine of 1? 0. What else has a cosine of 1? Two pi. So plus or minus 2 pi would work. What else? Plus or minus 4 pi. If we did pi, that would give you -1. What else? Plus or minus 6 pi, ... So if I were to look at the level sets, I would have something like this, where this is going to be the radius, square root of 2 pi. The next one would be, the radius square root of 4 pi. Now, is it possible for x squared plus y squared to be negative? No, x squared plus y squared is never negative. So only the positive signs come in. And so this is what the level sets are going to look like. And in general, if instead of giving you c equals 1, if I gave you c equals 1/2, you would again have a string of things where you could add multiples of 2 pi to it. So you can plot this using Mathematica. And so here are 2 different plots. The first is using plot 3D. And if you are doing this in Mathematica, you can actually touch the image and rotate the image. You can change what perspective you're looking down on it. It looks very rough. Part of this is because I'm plotting it in a square box Does this function really want x and y to be in a square box? No, it really wants things to be in circles. And so you're cutting some things off a little bit. That's why it's looking a little bit strange. Over here on the right is a contour plot. And I put in the plot legends automatic so you can actually look and see what is the value of the colors. And so you can really get a sense. So the brighter the color, the larger the value. And you can see this kind of periodic behavior. And you can see these rings, these circular rings where you're going to have roughly similar values. And the idea is, if you can do something like this, you can get a nice sense of what's going on. For a lot of times, we're going to be looking at staying on a level set. I want my input to be such that I'm on the surface f of x, y equals c. This might be, for instance, I want to stay on the surface of a sphere. I have some particle that's walking on the surface of a sphere and I want to see what's going on. So I might have some kind of constraints like this. And this is going to lead to the subject of constrained maximum minima. I want to find the largest value or the smallest value of my function, given that certain things have to be satisfied. And these are very natural things to have happen in real life. For example, if you own a business, you might have certain constraints about how much capital you have to invest. And you want to try to maybe maximize productivity, and you have to decide, how do I allocate capital to, say, labor, to supplies and whatnot. And there's a limited amount of capital I have to invest, and given that. Or maybe I have capital and labor to invest, maybe I can change those in certain regions, and I have to decide how I want to allocate them among different tasks. Okay, and then just one more picture. I love the command manipulate in Mathematica. So what manipulate allows you to do is it allows you to use a sliding scale to vary a parameter. So I'm manipulating C. And if you look, I'm doing the 3D plot as before, but now instead of just plotting cosine of x squared plus y squared, I'm plotting C comma that. So the constant function is probably the easiest function you can plot. So my function is, no matter what value of x and y you give me, the first function returns C, the second function returns cosine of x squared plus y squared. So this gold plane over here is just the function f, or maybe g of x, y equals c. And then by manipulating c, by sliding the scale, I can move this up and down. And so this is showing you, all the places it hits for a given value of c. I chose c to be 0.205. And you can see, yeah, it does kind of look like it's going to be circular intersections as it's going through. All right, so this is the high-level view of level sets. This is what I want you to be able to do in terms of understanding level sets. There is a lot more material in the book than I'm going to test you on or that you're going to need to do for this class, but it's good to be aware of what's out there so that in a future class, if you start to see some concepts that look a little confusing, you have to say, oh, okay, this seems similar to something I've done before. Let me go refresh and I have an idea of what to look at. Or I know that there's math that handles problems like this. I know what to go back to. So a lot of what I want to do is to just give you a sense of what's out there. If you want tests that are 6-7 times as long, I am happy to oblige. But as long as you can follow what I'm doing in class, what I'm giving you for the homework, that's fine. That's the level I want you to do. I want you to be aware of what else is in the book, but there's a tremendous amount of material in the book. So focus on what I'm doing in the lectures. Okay, any questions on level sets? Okay, so the next part is limits. So we've talked about limits before. So the definition of the limit is, we'll do something of two variables. Let's say we have a function f of x, y. It's defined near some point p equals ab. Sometimes we'd use the point maybe x naught, y naught to indicate the key point we care about. If you're really lucky, what would the point be? What would its coordinates be to make things nice? What's the friendly point we often use? Yeah, 0, 0. And so we say the limit as xy approaches p is L. What that means is you give me any tolerance epsilon. I can find a small distance delta such that as long as I'm within delta of your point, then the value of my function is within epsilon of L. So in one dimension, it's often done as follows. So here is my function. Here is maybe the point I care about, x naught. Here is the value of the function. And so that would be L, which would be f of x. And then what happens is you give me a small tolerance. You're moving at most epsilon above and below. And then the question becomes, which inputs of x will evaluate under f to being within that tolerance? And so over here, the way I happen to draw things, I can only go so far to the left, but I could actually go quite far to the right. And you take the smaller as your delta. Over here, I can only move a small bit to the left and still have f of x be within epsilon of f of x. I'm sorry, f of x naught. But I can move a great distance to the right. But I can move a great distance to the right and still be within epsilon. So it's a game. I give you a tolerance. I want to be within this much. And you tell me, okay, as long as I'm this close to x naught or closer, then when I apply f, I will be within your tolerance. You want to be within 1/10? Fine. As long as I'm this close, I'll be within 1/10. You want to be within 1,000th now? All right, I got to be a little bit closer, but I can still do it. You want to be within 1/1000000000? Stop doing this to me? Fine. I'll get even closer and it will still be fine. No matter how close you want it to be, I can always find a really small neighborhood of x naught so that I'm within that distance. And again, if you take an analysis class, you then do a lot of rigorous calculations to show that certain functions are continuous. And a function is continuous if its value at the point a, b is equal to the limit. So you've sometimes seen functions that are defined with a discontinuity. When I'm taking the limit, notice I'm talking about the distance from the point xy to the point ab, and I'm saying it's less than delta, but I'm also saying it's greater than 0. So that means I'm not allowing my point xy to be the limit point ab. This is very similar in calculus when we take the limit as h goes to 0, h is never allowed to be 0. If h was 0, we would be dividing by 0, and the numerator would be 0, the denominator would be 0, we'd have 0 over 0, we're not allowed to do that. So when we take the definition of the derivative, it's extremely important that h is positive or h is negative. It's just h can't be 0. So over here, similarly, when we're taking the limit, we're seeing what happens as xy gets closer and closer and closer to ab, but it doesn't have to be ab. In fact, it can't be ab. And if the value of f of x naught equals the limit, then we would say the function of one variable is continuous at x naught. Similarly, if the limit of a function of two variables is equal to the value of the function at that point, we would say the function is continuous there. And there's an obvious generalization if you go to higher dimensions. All right, the next is we have a bunch of limit laws. And so when we say the limit exists, we basically mean that the limit exists and it is not plus or minus infinity, that it's some finite number. And so we have the sum law, the limit of a sum is the sum of the limits. We have the constant multiple law. If I multiply a function by k, then the limit is multiplied by k. If you combine the constant multiple law and the sum law, you get the difference law. You take k equals -1. And so the difference law really just follows from the sum law and the constant multiple law. Then there's the product law. The limit of a product is the product of the limits. Then there's the quotient law. The limit of a quotient is the quotient of the limits, so long as the denominator is not 0. Okay, so these laws are exactly what you would expect. What you need to do is you need to formally prove that all of these satisfy this epsilon delta notation. And that's normally done in an advanced calculus or real analysis class. These are intuitively obvious. if f of x is how far, is how high I am above ground, and g of x is how high something else is above ground, and then I just plug one thing on top of the other, then my height should be the sum of the heights. If I convert from measuring things in yards to measuring things in feet, well, I should just then convert everything by that constant multiple of 3. If f of xy is approaching 7 and g of xy is approaching 8, then their product should be approaching 7 times 8. So again, these are all very natural things to hold. Okay. So the next one is, how do we find limits? So a lot of times we can do things by direct substitution. So for example, if I give you the limit as xy goes to 0, 0 of x squared plus e to the xy minus y over xy plus 2, how would we solve it? So x and y getting closer and closer to 0, 0 without ever being 0. What does the numerator look like? It's just 1. What does the denominator look like? 2. So I don't have 0 over 0. I don't have infinity over infinity. The denominator is not 0. I can just substitute in, and this is just going to be 1 over 2. So just replace x with 0, y with 0. So as long as things are nice, that's not so bad. What if I give you something a little bit more interesting? What if I give you, for example, the limit as xy goes to 0, 0 of, let's say, x to the 4th plus y to the 4th over x squared plus y squared. Well, L'Hopital is for a function of one variable. So for some problems, the simplest thing is if a limit exists, you have to get the same answer no matter what path you take. There are a couple of very natural paths to try. Can anybody think of some good paths to try? What would be a nice path to take? So I've got to look at all the ways xy can go to 0, 0. This is a 2-variable problem. Can you make it a simpler problem? So you've got to give me some way for x and y to get to 0, 0. What's the easiest way you can think of for xy to get to 0, 0? So one is to take x equals y. So one is to come in along the line y equals x. So that's one possibility. That's not the easiest, but that's a good possibility to check. There's something easier than y equals x. Or 2 things easier, in fact. So one is if y equals 0, so just coming in, and then, so this would be x equals 0, and then you had said y equals 0. So these are 3 very natural ones to try. And more generally, rather than doing y equals x, you could do y equals ax. And you could do a general line like that. Imagine you get the same answer along all 3 paths. Does that prove the limit exists? No. It makes you a little bit more confident. What shape could you try after a line? You could try a parabola, and after parabola, you could try a cubic. But you also have to remember, well, maybe I have some kind of like logarithmic spiral coming in, and I need to get the same limit no matter what path I take. And so just because you get the same limit along multiple paths doesn't mean the limit exists. It just means you start to get more and more confident. Okay. So now let's look at the path y equals 0. So if we look at the limit as x goes to 0, this is the curve, the path y equals 0. Well, when y equals 0, we get x to the 4th over x squared. That's the limit as x goes to 0 of x squared. What does that equal? Yes. And that's going to just be 0. And if I look at the limit as y goes to 0 along x equals 0, I'll get y to the 4th over y squared, which is just the limit as y goes to 0 of y squared equals 0. If I try y equals x, what will I get? I think this should have all been in red, actually. What would I get if I tried y equals x? So this would be the limit as x goes to 0, y equals x. I would get 2x to the 4th over x squared, which is just sorry, over 2x squared, thank you. And that would just be 2x to the 4th over 2x squared. What would that be? It's just, again, x squared. And as x squared goes to 0, what do you get? 0. In fact, you can show along any line it's equal to 0. So what do you think this limit's going to be? 0. Shall we try a parabola? Why not, right? Let's try the parabola y equals x squared. See which way I want to do this. And so if we try, so here is y equals x squared. We can take the limit as x goes to as x goes to 0 along the curve y equals x squared. We would get x to the 4th plus x to the 8th over x squared plus x to the 4th. Well, when x is really, really small, which is larger, x squared or x to the 4th? Goes the other way. If x is like 1/10, then x squared is 1 over 100. X to the 4th is 1 over 10,000. So x squared is much larger than x to the 4th. So really, when you look at this, the x to the 4th dominates the x to the 8th. The x squared dominates the x to the 4th. It looks like it's just x to the 4th over x squared again. And so this is a limit that you need to do carefully. I'll leave this as an exercise for you. Try to rigorously prove that this is still 0. At this point, we might be getting a little bit more confident that maybe the limit is 0. We've now tried parabolas. If I wanted to, I could come up with a limit which is 0 along any line, any parabola, any cubic, but not along a quartic. It is possible to have something that's really nasty. But at this point, we're starting to gain evidence, we're starting to believe. So now what we're going to do is we're going to use polar coordinates. So let's write x as r cosine theta, y as r sine theta, and as xy goes to 0, 0, we have, what does r have to go to if x and y are going to 0, 0? So if xy is going to the origin, what must the radius be going to? So remember, in polar coordinates, the radius is how far xy is from the origin. So if I give you, some point, here's the origin, and here is my point xy. That distance is r, and that angle here is theta. So if xy is approaching the origin, what must be true about the radius? It's got to be going to 0. And then theta is free. Theta can do whatever the hell it wants. As long as r goes to, so we can take any path we want. So this limit is the same as the limit as r goes to 0, theta is free to do whatever it wants. X to the 4th plus y to the 4th. It's going to become r to the 4th cosine to the 4th theta plus r to the 4th sine to the 4th theta over r squared cosine squared theta plus r squared sine squared theta. So it's the limit as r goes to 0, theta is free. What does the denominator equal? Almost r squared. And we have an r to the 4th upstairs. So we just get r squared times cosine to the 4th theta plus sine to the 4th theta. And now we can use the squeeze theorem. What can you tell me about cosine to the 4th plus sine to the 4th? How large could that be? Anybody know how large cosine to the 4th plus sine to the 4th is? It's okay to give me something larger than the true largest value. There's a very easy, it can't be more than this. Good, it can't be more than 2. It turns out it can't be more than 1, but it's easy to see it can't be more than 2. What's something that it has to be at least as large as? Can somebody give me a lower bound? I'm sorry? You could do -1, but you can do better because it's cosine to the 4th plus sine to the 4th. What's true about any real number when you raise it to the 4th power? Or it'll be non-negative. So what's your lower bound? It has to be at least, it has to be at least 0. So we know it lives somewhere between 0 and 2r squared. So if I now look at what happens as r goes to 0, what does 2r squared go to? So as r goes to 0, 2r squared goes to 0. And what does 0 go to as r goes? Well, that just goes to 0 as well. So this is the squeeze theorem. So no matter what this does, it's squeezed somewhere in between two things that are going to 0. It's greater than equal to something going to 0. It's less than equal to something going to 0. So what does it have to go to? It has to go to 0. And so that is the proof that x to the 4th plus y to the 4th over x squared plus y squared, this does go to 0 as xy goes to 0, 0. This is a really nice trick. Rather than trying to look at all the different paths, we can say, okay, there's infinitely many paths to look at. That's a lot to do. Let's look at this transformation. Let's put things into polar coordinates. Let's send r to 0, and then theta can do whatever it wants. And so for some problems, depending on what you choose for theta, you can actually get different limits. But for this one, we know it's at most 2r squared. We know it's at least 0, so it's going to be squeezed into 0. So as a nice exercise, you could try to come up with something where you would get a different answer depending on how you approach. If you did, instead of x to the 4th plus y to the 4th, if you did x squared minus y squared over x squared plus y squared, that would be a good example. Okay. And then the last thing I want to do is talk just very briefly about reviewing the notation for partial derivatives. So if we want to take the partial derivative at the point AB, one of the good notations is to use the subscript x. In Calc 1 and Calc 2, we often used prime. When there's only one variable in play, it's really not a big deal to use prime. I know I'm taking the derivative with respect to x. When I have several variables, I want to be able to quickly look at things and tell what's going on. Notation is extremely important. When you want to look at something complicated and be able to quickly read and see what's going on. Okay, the subscript x means take the derivative with respect to x. Is it possible that you could order your variables y, x, z? Absolutely. For those of you who are doing economics, what's on the x-axis? In your supply demand curves. Is it quantity or price? So quantity is the x-axis, price is the y-axis. So as the price increases, the quantity demanded decreases, right? Could you have price on the x-axis and quantity on the y-axis? Yes. You would then confuse anybody who's looking at what you're doing. You can do whatever you want. We know we standardize x is the first variable, y is the second, z is the third, or we use x1, x2, x3. The goal is to be able to quickly look at what's going on. This means take the derivative with respect to the first variable and hold everything else constant. F sub y is take the derivative with respect to the second variable and hold everything else constant. And so we can write it several different ways. We can write it as f sub x. We can write it as df dx. We read this as partial f, partial x. We can also put in a slash and then an AB, or put in an AB outside to just remind ourselves, where are we evaluating this? We're taking the partial derivative and we're evaluating it at the point AB. One of the abuses of notation is we'll often do is we might take the derivative with respect to x and then evaluate it at the point xy, just for convenience. Now, the next thing is, what if we take multiple derivatives? So you could take the derivative of the derivative. And if I first take the derivative with respect to x and then I take the derivative with respect to y, is that the same as taking the derivative with respect to y first and then with respect to x? So the notation, your f sub xy, is you read it from inside to outside. I first take the derivative with respect to x, then I take the derivative with respect to y. So what this means is this would be f sub x and then take the derivative with respect to y, whereas this would be f sub y and then take the derivative with respect to x. It's just notation. You could, of course, define it the other way around, but then you would be using the opposite notation of everyone else. Until you prove a major result that revolutionized mathematics and physics, you will use the notation everyone else uses. If you revolutionize science, we will adopt your notation. That's the rule. Okay, but for now, you want to just use what everyone else is using. You could have defined it the other way, but this is the way we've chosen to define it. Now, it would be wonderful if it didn't matter which order we differentiate. And so there's lots of different ways of writing it. So when I write fxy, I can write that as d squared f. So this is very similar to the d2f dx squared, the second derivative. That's what the 2 is standing for. And then I've got the dy dx. Oh, okay, so I put the dx furthest to the right, and then the dy after that. So I'm viewing this really as this is d by dy of df dx. And that's why I have dy dx in that order down below, because I'm taking the partial with respect to y of the partial with respect to x. It's a little bit annoying that that seems to be in the opposite order in which I'm seeing things over here. Welcome to life. I'm sorry. I can't do anything about this. This is way above my pay grade. Okay. So the last thing is, if everything is nice, if the functions fxy and fyx are both continuous, then you can switch the order of differentiation without effect. So then it doesn't matter which order you differentiate, you get the same result. All right. And so I'm not going to go into stuff like this, but it turns out there's a tremendous number of equations that are related to solving partial differential equations. And this is one of the reasons why we care so much about this. All right, so this is a good place to stop. Welcome back, everyone.